Volume and surface area. In all the previous geometry that we've talked about, all the lessons up till now, we've been looking at 2D figures, that is to say flat things that would just be drawn on a two-dimensional surface. Now we're going to look a little at three-dimensional geometry. In 2D, we could talk about the area of shapes. In 3 dimensions, we will also talk about the volume of shapes. We'll start with the easiest 3D shape, the cube. The cube, of course, is very special, much in the same way that a square is special among quadrilaterals. A cube is special among 3D shapes in many ways. So what's true about a cube? Well, first of all, it has 6 faces, and these 6 faces are 6 congruent squares. It has 8 vertices, that is to say 8 corners. It has 12 edges, 12 congruent edges. Those edges, of course, are the little line segments that connects vertex to vertex. And it is true that the faces meet at right angles at the edges, and 3 mutually perpendicular edges meet at each vertex. So these are the properties of a cube, very special. If a cube has an edge length s, then its volume is given by v equals s cubed. When we raise a number to the 3rd power, we call this cubing the number, precisely because this is how we find the volume of a cube. So both the algebra term to square a number and the algebra term to cube a number, these are terms that have their historical roots in geometry. Each face on this cube is a square with side s, and so it would have an area of s squared, and that means that the total, because there are 6 faces, the total surface area of a cube would be 6s squared. The cube is a special case of a more general category known as rectangular solids. The sides can be any rectangles, the faces, but we still have the requirement that the faces meet at right angles at each edge and 3 mutually perpendicular edges meet at each vertex. So most boxes and cartons are rectangular solids. The world is just absolutely full of rectangular solids. The volume of a rectangular solid is the product of the 3 different edge lengths. So we call those lengths height, width, and depth. The volume is just the product of those 3. The surface area, well, this is tricky. We compare the rectangles because, of course, opposite faces are congruent. So we have 2 rectangles that are h times w, that's the front and the back. We have h times d, that's the right and the left side. And then w times d, that's the top and the bottom. And so then we add all those up for the total surface area. I would urge you not to memorize this as a formula. I would urge you just to think through the process of finding the areas of those rectangles and adding them up. In a rectangular solid, we can consider 2 different kinds of diagonals. One kind, called a face diagonal, is a diagonal of only one face of the solid. And of course, we can always find this length with the Pythagorean theorem. We just use the 2 edge lengths. Those are, of course, the 2 legs of the triangle. So here we have a 3, 4, 5 triangle, and AC equals 5. The other kind of diagonal, called a space diagonal, does not run along a face. It passes through the interior of the rectangular solid from one vertex to the opposite vertex. So this is a little harder to visualize. This is going from vertex A through the center of the figure and coming out at the opposite vertex at D. And so for this, we use a 3-dimensional version of the Pythagorean theorem. So it's actually edge squared plus edge squared plus edge squared. As long as those 3 edges are all perpendicular to each other, then we can square all 3 of them, add them together, and that will equal the square of the space diagonal. So here we get 3 squared 9, 4 squared 16, 5 squared 25. Add them up, we get 50. So it means that AD is the square root of 50, and of course we can simplify that to 5 root 2. And so 5 root 2 is the length of that space diagonal. Now the test is probably not going to use the term space diagonal, but it will give you that. For example, it might give you that diagram and say find the length of AD, and so you're going to have to know how to do this. What is the length of the space diagonal of a cube of edge length S? Well, again, we'll use the 3D Pythagorean theorem here. And of course, we have 3 edges, each with a length of S. So AB squared is just going to be S squared plus S squared plus S squared, which of course is 3S squared. Take a square root. And what we get is that AB is the square root of 3 times S. So this is interesting. The diagonal of a square is root 2 times the side. The space diagonal of a cube is root 3 times the side. Very interesting. And the test loves that little fact. Here's a practice problem. Pause the video and then we'll talk about this. Okay, so we're given 2 of the 3 edge lengths. We have the 4 and the 6. We don't know the length from front to back. We're missing an edge length there. But we are given the length of the space diagonal, JK. And we need to find the volume. So the first thing we need is we need to find that missing edge length. So call that D, the depth. We don't know that. 4 squared plus 6 squared plus D squared equals 8 squared. And so 4 squared plus 6 squared, that adds up to 52, plus D squared equals 64. D squared equals 12. Take a square root, D equals the square root of 12. We can simplify that to 2 root 3. If all this stuff about simplifying square roots is unfamiliar to you, I would strongly suggest go back and watch the video in Powers and Roots on simplifying square roots. That would be very important to appreciate before you understand all the square roots in this lesson. Well, now we have our missing edge length, so now we know all 3 edges. So of course the volume is just the product of those edges. Multiply this together and we get 48 root 3, and that is the volume. Another 3D shape that the test could expect you to know is the cylinder. The cylinder, when resting on the circular base, has a height of h. The radius of each circular base is r. So there are 2 congruent circles at the top and the bottom, and then this curved side connecting them. That's a cylinder. So the volume, you can think of it as just the base times the height. And of course the base is a circle. So that's pi r squared, the area of the base, times the height, pi r squared h. That's the volume of a cylinder. The total surface area of a cylinder is interesting. Obviously, the circular top and bottom are easy. Each one has an area pi r squared. That's the easy part. Think about the curved side, what is called the lateral surface of a cylinder. Think about the paper label on a metal can. If we cut the label vertically, we can unroll it into a flat rectangle. So imagine that we do that. We cut that lateral side and unroll it into a rectangle. And so the whole area of the surface area of the cylinder would look something like this. We have the circle at the top and the bottom. Those are the pi r squares. We know that. And then we have that long rectangle. Now think about that rectangle. The top edge of that long rectangle, so the edge right here, that had to run around, that fit neatly around the top circle. And so what that means is that edge must be exactly as long as the distance around the circle. And of course the distance around the circle, that's the circumference, 2 pi r, so it means that the top edge of that rectangle is 2 pi r. Well, now we know, we have the height already as h, we know the base and the height of the rectangle, so that lateral area, the area of that rectangle, base times height, 2 pi r h. And then we can add that to the 2 circles. The total surface area is pi r squared plus 2 pi r h. Once again, I will ask you not to memorize that formula. Please understand the logic that we talked about and why this formula is true. The only other 3D shape I will mention is the sphere. You don't need to memorize anything about it. You simply need to know what it is. So here's a picture of a sphere. Every point on the surface is equidistant from the center. The sphere is circular in every direction. And one way to think about it is the surface of the Earth is roughly a sphere. So you could walk around, obviously you can't walk all the way around the Earth, but for example, you could fly all the way around the equator, you could fly over the prime meridian, the North Pole, then down around the South Pole. So there are a bunch of circles you could make in every direction, and you'd always come back to the same place. Here's a practice problem. Pause the video, and then we'll talk about this. A cylinder neatly encloses a sphere, so that the curve of the cylinder touches the sphere in a circle at its widest, and the top and bottom faces of the cylinder are tangent to the sphere. If the volume of the sphere is 4/3 pi r cubed, what fraction of the cylinder does the sphere occupy? Well, this one requires a lot of visualization. Let's think about this. First of all, the radius of the sphere and the radius of the cylinder must be the same. That's how they touch each other all the way around that circle at the middle. So they have the same radius, we'll just call that r. The height of the cylinder must be as tall as the sphere. So in other words, its height must be the diameter of the sphere, and of course that diameter would be 2r, so h equals 2r. So now the volume of the cylinder, of course it's pi r squared h, or pi r squared 2r, and we can just simplify that to 2 pi r cubed. Well, now we're going to take a ratio. The sphere is taking up what fraction of the cylinder? Well, we're going to divide 4/3 pi r squared by 2 pi r squared. Of course, the pi r squareds will cancel, and we'll just be left with the numbers. 4/3 divided by 2, or 4/3 times 1/2. And that is 2/3, and that's the fraction that the sphere would take up of the cylinder. That fact was very important to Mr. Archimedes. He actually put it on his tombstone. In summary, for the cube, we have a formula for the volume, V equals S cubed, and the total surface area, 6S squared. For a rectangular solid, it's important to know how to find the volume as well as the surface area. And for a cylinder, it's very important to find the volume as well as the surface area.